Hello students and welcome to a new chapter about gases. The elements expressed or highlighted in the blue color here are those elements that exist as gases at room temperature and 1 atmosphere. That includes hydrogen, the noble gases, nitrogen, oxygen, and from the halogens we have fluorine and chlorine. Physical properties of gases, they do assume the volume and the shape of the container. So they don't have a given volume or a constant shape. They rather will adapt to the shape and the volume of the container they occupy. Most compressible state of the matter, and that's simply because gas particles are separated by large distances. So this is here what's is like empty space between them, and therefore because there is a lot of empty space between them, I can compress them. I can put pressure on them and make them go close to each other. They will mix evenly and completely when confined in the same container. If I have two gases and I put them in a cylinder, they will definitely occupy and mix together, occupy the whole volume of the cylinder and mix together in a homogeneous way. In another word, they will make a homogeneous mixture. And they are definitely much lower densities than liquids and solids because there is a lot of empty space between them. In a given volume, there is a very small amount of mass. And remember, density is mass over volume. Therefore, for gases, I express the density gram per liter. However, for solids and liquid, we do express it as gram per milliliter. Milliliter is such a small volume to have a significant amount of mass for gas. That's why I needed a larger volume when it comes to gases. Pressure is another thing I normally talk about when I talk about a gas. Pressure in physics is defined as force by area. However, when it comes to gases, I want you to think about the pressure as the collision of the gas particles with any surface that they hit, right? So gas particles are moving very fast, and while they do in a room, for example, they were going to collide with the ceilings, with the walls, with the floor. The pressure comes from the fact that they are colliding and they are hitting the ceiling. That's why they are exerting pressure on the ceiling. They are hitting the floor. That's why they are exerting pressure on the floor, and so on. More collision, more pressure. The more collision any surface is experienced from a gas, the more pressure it will experience as well. So if you look at these two containers, you have less amount of particles colliding with the container walls, so that will be lower pressure. There is an L here that is missing. It's lower pressure. And on the other picture, it's a higher pressure because I have more particles colliding colliding the walls of the container. Okay. The harder strikes, the more pressure. So, a weaker strike is lower pressure. A harder strike is definitely going to give me more pressure. When it comes to the atmospheric pressure, we said that, pressure is force over area. There is a column of air above the surface of the earth. That column of air will cause a pressure on that area. And that is what we call the atmospheric pressure, because that column of air is coming from the atmosphere, which is where we have the air, okay? Where we have the gas particles that are making the air. So the atmospheric pressure, by definition, it's the pressure exerted by the Earth's atmosphere. And there is a gravitational force that causes a certain pressure at the sea level, now, which is 1 atmosphere. Now, if I go higher than the sea level, that column is going to get shorter, which means I have less force on that area, and therefore the pressure will drop to 0.5 atmosphere. And if I go even higher, that column gets shorter and shorter, which means less force on that area, which means less pressure. And that is 0.2 AM. ATM means atmosphere, right? Which is a pressure unit that we use to express the pressure of the gas. So now, if I am gonna draw this for you guys, and that is an easy way to draw it. If this is the valley, this is the sea level, and this is the top of the mountain, let's draw the column of air coming from the atmosphere, right? If the atmosphere, where the gases end right here, this is the column on the mountain, this is the column on the sea level, and this is the column on the valley. And there is a higher, bigger column on the valley, so that is a higher pressure. And there is a shorter column on the mountain, and that will be a lower pressure. Units used to express pressure. The SI unit is Pascal, which coming from Newton per meter square, right? Force is Newton, meter square is the area. Also, atmosphere. And 1 atmosphere is defined to equal 760 millimeter mercury, which equals 760 torr, right? What does that mean? That 1 millimeter mercury equals 1 torr, which also equal to 101,325 Pascal, which is also equal 14.7 PSI. And this is pound per square inch. This is the American unit for expressing pressure. Please make sure that you take a note of these conversions, as you will need them in this chapter. The standard atmospheric pressure, which is the 1 atmosphere, is the pressure that supports a column of mercury exactly 760 millimeter in height at 0 degrees Celsius at sea level. So, this is here an instrument we call the barometer, which is an instrument designed to measure the atmospheric pressure. Please take a note of that. This is designed to measure the atmospheric pressure. And if I have an evacuated tube immersed in mercury container, right? The atmospheric pressure is going to press high for the mercury to come up. And that amount of mercury right here that came up, that is H here, that is equal to the strength of the atmospheric pressure. So here we have vacuum, right? There is no air here pushing back. There is vacuum, nothing in here. So that height is equal to the strength of the atmospheric pressure. And therefore, that height will be equivalent to the atmospheric pressure, and when we measured it, it was the 760 millimeter mercury. Now, this is a different device. We call it manometer, and the manometer is used to measure a gas pressure in a sample, not the atmospheric pressure, that is the pressure of the atmosphere. No, this is you having a sample, and that sample of a gas will have a pressure. How much is that pressure? So if you look at the design of the manometer here, before we allow the gas to escape, let me have a simple drawing here for you guys. Right? There will be mercury level, they will be equal here. Now, this is a gas, and I will have a stopper. Once I open the stopper, right? So let's open the stopper. Let me now open the stopper. Right? Once I open the stopper, the gas is gonna come out and it will exert pressure. That pressure will make this mercury level at this side to go down. The amount it's pushing it down is H here. And if I can take a ruler and measure this height, that will be that it's in mercury, right? So I measure it in millimeter, and let's say I read 72.7 millimeter mercury. That is the amount of the pressure of the gas. So if I am measuring the gas pressure, it will be 72.7 millimeter mercury. Now there is that we call this one a closed-ended because this end here is closed. There is another type of manometer that we can look at. Which is when we have an open end. If you look at this end right here, it's open to the atmosphere, right? So in this case, there is a competition from the pressure of the gas and it's open to the atmosphere, so the pressure of the atmosphere. And in this case, whoever is stronger will push the mercury down. If you look at it, because they normally started at the same level, they started here. However, this here was stronger, so it pushed the mercury down, and it's pushed it by H. What does that mean? It means that the pressure of this gas is stronger than the atmospheric pressure by H. So when I want to calculate the pressure of this gas, it will equal, in this case, the height and the atmosphere, right? Because it was, to start with, if it was equal to the atmosphere, no movement will be like observed, which means the gas pressure equal the atmospheric pressure. The fact that the gas pushed mercury down, it means it was even stronger than the atmospheric pressure by H. So when I want to now express what was the gas pressure, it will be H, I'm going to have to measure that by a ruler, plus the atmospheric pressure. And this is what we call the open tube. And in this case, the gas pressure is larger than the atmospheric pressure. And this is how we measure the pressure of a gas or a sample in an open-end manometer. That's it for this introduction, and I will see you in the next lecture.